Um, okay, so today we're happy to have Ben Lillard from Oregon. Ben did his PhD at Irvine with Tim Tate, and then went on to UIUC for his first postdoc, and now he's wrapping up at Oregon and is going to be joining. Well, maybe it's
Yeah,
still in the
nothing
works,
official
right?
yet.
Nothing official, but we'll be migrating to another position here in a little bit. So Ben is going to be telling us today about exciting new directions in dark matter detection. So
Yeah,
take it away.
Thank you so much for having me. It's a real pleasure to be visiting here in Minnesota. I've been to your city before, but not officially to your campus. So it's a pleasure to be here for that as well. Today, I'm really going to be focused on direct detection and how new experimental techniques and theoretical methods can be used to enhance the search for dark matter. The talk will encompass some discussion of experimental design even, although I am a particle theorist, I even had to learn some physical chemistry in order to make the predictions I needed to. So I will even get as far as explaining what these hexagons are and what I had to do to them as a theorist to uncover some aspects of the electron wave functions. One of the results and the main motivation for looking at such a complicated system is that the dark matter scattering rate in my detector will become a function of time that varies over the course of the day. There's various examples that all depend on the details of the dark matter model, its particle mass, its interactions with the standard model. And we're going to be able to use this to distinguish between the dark matter signal and all of the sort of standard model backgrounds that you would tend to expect in this low energy regime where I will be working. So the brief outline of my talk in pictures is, first, I will talk about dark matter in the context of the Earth and a laboratory that is designed to stay on Earth. I'll talk about the rotation of the Earth and how this is a useful thing. Following that, I will describe physical chemistry in just the barest amount of detail necessary to a particle theorist. My results will involve some plots that look like this in box number 3. This will be some sort of response of my physical detector to dark matter. And then lastly, I will show some ongoing work that's centered at Fermilab, but involves many other institutions using large crystalline detectors. There's an ongoing prototype being built at Fermilab at the 8-gram scale. And throughout all of this talk, I'd like you to keep in mind that it's very easy to get kilogram-sized samples of these materials that I'm going to talk about. The current state of the search for dark matter with direct detection, often we can think of this as starting with the WIMP dark matter, with nuclear recoil. So in a WIMP model, the dark matter may be some sort of electroweak multiplet, and it communicates to the standard model, say through scattering with a Z boson or a Higgs, possibly some loop involving W bosons. But the dark matter is neutral and it's weakly coupled. So it satisfies all of the experimental constraints, except for the last decade or two worth of direct detection experiments. If the scatterings occurs directly through a Z boson, for example, then the cross-section was so large that it was not even on this plot anymore. So if the scattering occurs through a Higgs directly, then we also have good constraints on that. But there are still some WIMP candidates with cross-sections that are low enough that they would even start to blend in with the neutrinos. Say if dark matter is a Higgsino, for example. So the experimental, the great drastic leaps forward in experimental sensitivities have been entirely due to the fact that these experiments are very much background free. You can put multiple tons of liquid xenon in a tank and see very few events with the right sort of energy spectra to have come from dark matter. So if you make your detector 10 times bigger, you become sensitive by another factor of 10 on this plot. once these experiments start seeing neutrinos, that linear progress is going to slow. Well, slow to a crawl at first, and then only proceed beyond this limit with drastically larger detectors. We were already reaching that limit of experimental sensitivity now. We have recently discovered some solar neutrinos at low energies, these ones here, in both xenon and the Panda X experiment. So we're already encountering this neutrino fog, and that's going to make it hard to make fast progress in this part of the parameter space. Now, this is all with nuclear recoil. If dark matter is somewhat lighter in mass, then these nuclear recoil experiments are not particularly sensitive to their scattering. One would need to go to lower energy detector kinematics in order to even resolve such an event. So there's both because of this and because of the fact that the leading experiments are tiny in comparison, comprising only a few grams or tens of grams rather than thousands of kilograms. The constraints, if I put them both on the same log-log scale, are orders of magnitude weaker. This experiment that's currently being built, DOMIC M, has 1 kilogram, or it plans to have 1 kilogram worth of some complicated semiconductor material. And even with that effort, we're not even approaching the same sort of cross-section in centimeters squared that's being probed in the nuclear scattering.
But there is dark matter reflected from the sun constraints from the same xenon, right, which covers a lot of white space.
This is true.
That you don't put that in.
Yeah. Yes. And xenon, these experiments do have sensitivity even through the scattering off of the electrons without the solar reflection. So the solar reflection can help by boosting the velocity of the dark matter. If it, say, thermalizes with the sun, it can become faster than you naively expect from just a dark matter in our vicinity. Xenon can also look for an electronic-only signal for dark matter that couples to electrons. And that gives sensitivity down to 50 MeV or maybe as low as 20 MeV.
Well, if
yes.
you take the reflected flux and 1 MeV mass, right,
Mhm.
the limit on the cross section is better than 10⁻38. If this is like in the middle of the white spot.
Mm-hmm. Yeah, no, this is true. Yeah, the solar reflection constraint is not on this plot. Yeah. So, good. Yes. So, for all of this discussion, I was describing nuclear scattering. For the remainder of the talk, I'm going to focus on electronic scattering. The reason for this is because it's very difficult to get a nuclear system to respond with energies less than a keV. The kinematic threshold for nuclear recoil is maybe more like 2 or 3 keV. And due to the kinematics, it's simply very hard to excite a detector if the dark matter mass is less than a GeV. This is a simple statement about the velocity of the dark matter, which, if it comes directly from the halo, is constrained to be something like the escape velocity of the galaxy, plus the Earth's boost with respect to that galaxy. If I plug in the kinematics for the dark matter mass m and the energy delta E that's required to excite my detector, I find that for a 1 keV energy transfer, my experiment is completely insensitive to 300 MeV dark matter. So in order to fix this, I either need to go to faster dark matter or lighter, lower energy detection methods. And switching from nuclei to electrons is a perfect way to do this. Unlike nuclear systems, the characteristic energy of an electronic system is electron volts, 1 or a few. This is the regime of visible light. Even for ultraviolet processes at 10 eV, my mass threshold goes down to 3 MeV, 2 orders of magnitude lower. This opens up rather a lot of space on my log-log plot without negatively impacting the high mass limit. So if we could build all of our detectors to be sensitive at these energies, we would win without losing it. This is almost true. It's true from if we have to ignore the theoretical difficulties involved with these calculations. This is not an experimental expense, but it is a theoretical one, which is that electrons don't like to just form free gases. They like to live in bound states. And the description of chemists is entirely focused on describing these systems. So we'll have to learn a little bit of chemistry in order to do physics. Before I proceed with that, I'd like to talk a little bit about the particle models that actually live in this parameter space. It's nice to show a big parameter space plot, like these ones that come from one of my papers. But if we've ruled out a certain point on this plot, we'd like to know what this tells us about the higher energy physics at the more fundamental level. So there are a couple of popular production mechanisms for dark matter in this limit. One is familiar from the WIMP dark matter. It's freeze out. This is assuming that back in the early universe, the dark matter and the standard model were in some sort of equilibrium. They scattered, there were number changing processes back and forth. And then at some point, the universe has cooled down and expanded so that the dark matter can no longer find an anti-dark matter to annihilate against. So this process going from dark matter to standard model slows down. And the point at which it stops is controlled by the dark matter mass. And so that sets this sort of freeze out line once you've picked a particular model, say scattering through a heavy scalar mediator, where at every point along this line, there should be some, in this case, simple mechanism that tells us how much dark matter should there be. And it happens to match what we observe. Another popular model, especially at these light masses, is freezing, where it goes in the opposite direction. Rather than starting with an abundance of dark matter in the barrier of the universe, you start off with essentially all of the dark matter has to be produced from the standard model itself through scattering. So the standard model plasma is hot enough to produce dark matter, say through a vector boson, some other sort of light mediator.
So I don't
Yes.
understand your line. So the freezing models typically have much smaller coupling than pre-dark models.
Yes,
And
absolutely.
Why are there sections that are roughly similar to 10⁻36?
Yeah. So in this case, it's entirely because my mediator was light. If I showed you the same sort of process with a heavy mediator over on this plot, the freeze-in line would be somewhere down here. It would be incredibly tiny. So in this case, the scattering is happening through a mediator that is suppressed at high momenta transfer and enhanced.
In my mind, the model with the dark photon mediator, and then in that case, I know that for a fact that this is much lower. So
Yeah.
it must be very model dependent.
Yeah, very dependent on the mass of the mediator. So for this, yes.
Masses dark photon people, that line, as far as I remember, much lower.
For the freeze-in, well,
Yeah.
That's also depend on the coupling. too, right?
No, you choose the
it's-
coupling, so you produce just enough dark matter, right? And then now the couplings are fixed, right? You go and calculate, it's 1-to-1 calculation, because there is no mass to a mediator involved. So it's well-defined person.
Yeah.
Are you sure about that?
yes, yeah. Well, not about this slide, actually. Robert will be the first.
Yeah,
He was
I
the first to
gonna
tell me
say-
that there is actually a mistake in this part of it. Robert will like this plot better, I think.
I
Yeah,
think it's
that's-
gigantic cross-section.
Yeah, no,
Yeah,
yeah, that's.
but yeah, in this case, a light mediator. Yeah, in this case, the light mediator means light compared to the momentum transfer, which is about a KeV in this case. So if it's a sub-KeV mediator, then That's what generates this lower freezing line. The dashed line is what I have from what Robert called previous work. That's the plot that I digitized back in 2021. But going forwards, Robert tells me we should use this line instead. Right. You told me in Mainz already, but I remembered.
Can you actually have
Yeah, you don't want it to be massless exactly, because
there won't be a problem with that, but if there's a dark quadrant, you know very well, then it's strictly massive, it's not produced. Because of the.
Yeah, I get it. So if it's really the massive one, do we really only make dark matter and no additional things on this?
oh, okay. I actually didn't realize that that was an option. Yeah. I usually don't like perfectly relativistic species in my early universe.
Yeah,
Okay, yeah, so the sort of effective charge goes to 0 in that limit. Under the dark matter you want.
yeah, the effective charge of those. You need the
Mhm. Yeah.
I see that other people with that line state 7. One and.
Oh yes, sorry.
Oh, yeah.
My plot wasn't aligned in this one. Yeah. So yeah. Aligned the rectangles without aligning the parameter spaces.
Sorry, you're saying that this is solid lines already.
No, actually, these were projections from my trans-stilbene. Yeah. So soon, we hope to do this. We hope to do this with 1 kilogram of trans-stilbene. But we're not there yet. So good. So I think I'll move on to discuss how to design an idealized detector for this system. So I'd start with 3 criteria. I'd like a low energy threshold for this parameter space. I'd ideally like a high density. That is, if I have to instrument an entire room to have a kilogram of target mass, that's a fairly difficult endeavor. I'd rather have my kilogram occupy a small. And I need to have some measure of transparency. That is, if I create a signal in the middle of my detector, I need that signal somehow to propagate to the edge so that I can count it. There's a couple of kinds of matter that exist in this world, and one of them is rocks. Rocks have a sensitivity to ultraviolet light. They have a good density of 3 in whatever units you like for density, but they're not transparent. If I created an ultraviolet photon in the middle of this, it stops immediately. It scatters far too many times. I would have to take the rock, cut it apart, and then put it under an electron microscope to see that something had happened. And that's exactly the point of the task. There are prospects for doing that, but it takes a long time to actually measure a gram's worth of the sample. Next, let me consider water. Water also has sensitivity at the 10 eV scale. It's got a decently high density, but water is unfortunately not transparent. Not transparent in the ultraviolet, that is. It's perfectly transparent for blue light, red light, but right at 10 eV, it becomes very opaque. The mean free path of a 10 eV photon is less than 100 nanometers. So unless I want to put my detectors 10 nanometers apart inside my volume, water is no good. Gas is another form of matter. It has a low density, which is a negative, but this helps with the mean free path. If my gas is dilute enough and a dark matter event creates some sort of a photon, there's a better chance that that photon makes it to my photon counter. The downside is that to get, say, a ton worth of mass, you need to instrument many, many thousands of cubic meters. So.
What you really care about is like the number
Yeah,
It's not like actually, but between different solids, the main thing that in my mind is the size of the.
no, you're
but
absolutely
that's
right.
okay,
Yeah,
right? Like gold is not.
that's true. Yeah, if I'm really, I want to track the electron number density in my material. Yeah, if I'm scattering off of electrons only. So, good. That said, for the two best examples I have here, semiconductors and scintillators, the electronic number density is also, the relevant electronic number density is higher in silicon and germanium than it is in metal. So this factor of 3 is correlated. Both of these are transparent in the way that it counts. For semiconductors, if you create some sort of an electron hole pair somewhere in the middle, you can pull that to the side of this detector by applying some E fields. This is exactly how a digital camera works. So in my very simplified picture of these detectors, you take the TCD off of the back of a bunch of cameras, and you put them all into a box, and you try to get a kilogram of that. The way that the scintillator works is it does something fancy that water does not do. It shifts the frequency of the ultraviolet light into the visible. So if you shine ultraviolet light at any of these samples, you get blue light back. And that sort of transparency is called fluorescence. So if you were to say shine a 4 eV photon at the sample, there are some transitions, non-radiative ones within the molecule that can shift that energy downwards and to scatter to a slightly different state near the ground state. And this can be enough to shift that frequency by a factor of 2, from 4 eV down to 2 eV. In order for this to work, you want the absorption band of the material to be offset from its emission bands. And so the chemical that is in that photograph is trans-stilbene. It's a very efficient scintillator. The one in this picture is called anthracene. It is one of the most efficient, such that all of the other chemicals are usually labeled according to their relative efficiency compared to anthracene. So trans-stilbenes is about 80% in that measure. Anthracene is so efficient because there is virtually no overlap between the emission and absorption bands. So we're looking for some sort of a detector system like this. I'd like to add a fourth criteria now, which is that in this regime, if there is any background, I'd like to tell the difference between background and my dark matter signal. This is especially important at these low energies because all of the detectors that have been built so far in the sub-GeV mass range see some sort of a low energy excess. In the case of Sensei and Domik, they see it in their 1 electron bin. In the case of some other ones, they just can only count numbers of events, and they see some non-zero number. So,
Yeah, very, politically correctly framed. Right?
yes, yes.
You can call it nothing works.
Yes.
More appropriate, I think.
Yeah. So for something like Sensei, they can count the number of electrons that were excited from a single event. And if they look at the 3 electron bin, then they see really no events. If they look at the 2 electron bin, they see some events, but it's a small number, small enough they can set some decent constraint. And in the 1 electron bin, there's just thousands of events, maybe 10,000. So it's entirely the opposite of the regime in which Xenon and LZ and Panda X work. And so that's why we need something different. And for this, I have to take a step back to think about the galaxy again, or for the first time in this talk. We live partway through this disk of stars. We're going this direction, clockwise, if that means anything, towards the constellation Cygnus, if you know where that is on the sky. And we're collectively traveling in that direction at about 250 kilometers a second. That's the velocity of the sun. It's a little bit offset from the velocity of local standard of rest. And if you talk to an astronomer, they'll know what that means. And of course, the Earth orbits the sun. It's something like 23 kilometers a second. That velocity is a little offset from this velocity vector, and so it changes this number by about plus or minus 15 kilometers a second every year. There are some proposals to use this as the means to distinguish standard model background from dark matter, but it's a tricky proposal because if you see a signal, there's nothing you can really do to your detector to change the phase of that. You just wait for another year, maybe you see the same thing. And so that's why I'd like to think about the dark matter wind. So because we're traveling so fast in this direction, there is an effective wind of dark matter that we expect, at least from the standard halo model, to be incident upon us at about 250 kilometers a second. Where Cygnus changes on the sky over the course of the day. And so the direction of this dark matter wind also changes every 24 hours, or rather every 23.93 hours. This is called a sidereal day, due to the need to actually rotate the Earth by 360. Now, if you had a directionally dependent scattering rate, then this rotation would give you a modulation on that same frequency. And it's fairly difficult to imagine a standard model source that happens to oscillate on the sidereal. But we can talk about that again in a minute if you still curious. So what's happening today here in Minneapolis, I checked the parameters of the dark matter wind. I actually checked this yesterday. At about 10 o'clock this morning, the dark matter wind was almost directly above us at about 89 degrees up. So it was also a little bit south by about 1 degree. So this is what the dark matter was doing at 10 o'clock. But over the course of the day, it's going to rotate about the North Pole, which is an axis rather like this. So every 24 hours, that wind will modulate like this. It'll go from south to west, to northwest to north, and then at midnight, or rather 10 p.m. tonight, it'll be basically along the horizon, slightly below. That's the expectation for what the dark matter wind is doing now. So if we were to build a directionally sensitive experiment and put it on the table so that its maximally sensitive direction is pointing up, we could expect to have a large modulation in our detector. In order to fake a signal like this, you would also have to get the phase correct. You'd have to have your weird standard model background also peak at 10 in the morning and reach its minimum at 10 p.m. If you were to do this experiment 3 months later, this time should shift by about a quarter of a day. So there's a lot of tests you can do without changing the setup in your laboratory at all. So this is a tremendous help when cutting through an irreducible background, if you have a material that modulates with an amplitude large enough. So this is a little bit of a sneak peek, but we've done this calculation for trans-stilbene, and at low maxes, you can get even plus and minus 40% modulation in the rate, or I should say plus 40% minus 30% for, say, a 2 MeV dark matter candidate. In the case of a light mediator, you even see plus minus 15% even at arbitrarily high masses. Yes. Oh yes, I haven't forgotten about the dispersion at all. Of course, if I treated the dark matter as a laser, like I have in this picture, yeah, that's a very unrealistic thing to do. It would give me an even bigger modulation. In this case, I put in a dispersion that was the same as the local the local standard of rest. Here, I believe we use 238 kilometers a second. That's the same basic number as the overall wind velocity. So
that's the simple one. So it's an ensemble operating ensemble, so it's
Mhm.
for any real measurement, just from the dispersion factor alone, to have a huge
so I've done the integral over that dispersion.
What's it now?
Yes, yes, so the central value is at about, 252 kilometers a second. Yes, the band is 238 for this model.
Yeah, in this plot, I want to ask you, what's the one sigma band, the amplitude where that matter comes from?
Ah, I see. So I've taken one particular standard halo model, and it includes this dispersion of 238. In this model, the dark matter velocity distribution is approximately a Gaussian with the central value in this width. In order to actually calculate the rate, I have to integrate this against my momentum response function of my detector. It's some big 6-dimensional integral. And I do this and I get one particular prediction. So that's why I have a line in these plots. Now, I could also vary the parameters of my model because we don't actually know that the dark matter wind velocity is exactly centered at 252 kilometers a second. There's some systematic uncertainty as well. So if I accounted for that systematic uncertainty, that would give me a band here due to just changing the parameters of the astrophysical model. Not necessarily. No, I'm not using the central value. I'm doing a whole integral.
The local and central dark matter randomly starting anywhere, when you have an average velocity of 20-30 kilometers, they have all of that. You want to put it.
Oh yeah, no, it's a huge thing. And so what I've plotted here is the average rate of the function of time. And so this is what I would get if I were to measure, say, 100 events, or 10 even. So that would give me one version of this average. Yeah, I'll have some plots that will add the systematic uncertainty, but there's no, yeah. Okay. Yeah. Here.
So, yeah, you said that the, for like the top, the dispersion is 230?
Yeah, we usually use 238 at the moment, yeah.
But you're looking for a change in the signal of 22 over the course of the day?
This is the signal, this is the change in the signal that is left over after I do that integral over the full distribution. So I may skip ahead to just show the integral that I'm actually doing. This may help clarify things. So the velocity distribution, yeah, this is effectively a velocity distribution once I put in the kinematics of the dark matter. This is a thing that has that dispersion that we're discussing. I also have some sort of a response function for my chemical system as a function of the momentum transferred into the system. And so this is an integral that I have to do for one particular dark matter model. And it's the result of this integral that gives me my average rate of sequential time. So that takes into account the fact that any gigantic signal I would have had from laser dark matter has been averaged over by the large dispersion. And so it's actually rather remarkable that I still have a 20 or 40% modulation left over after I've done this integral over the velocity dispersion.
Even if you had laser dark matter,
Yes.
like there's still some probabilistic. Like if you see an event, you can't go back.
This is absolutely true. Yeah. Yeah, the only information I have from this version of the detector is the number of photons I found. And so, and I can't even trace the kinematics of that photon back to the source because it's scattered multiple times in my detector material. So, yeah, so I can't reconstruct the free momentum of this momentum transfer. And so, yes, even if I had a laser dark matter, I wouldn't necessarily be able to have a laser version of the output. It would still be scattered over a full 4 pi of angular degrees of freedom. Yeah.
Really, the only information
That's right. Yeah. Even if there were some sort of a directional variation in that outgoing rate, the outgoing photon, usually in these materials, it scatters multiple times at least, dozens possibly. And so after all of that random walking, there's no way I could trace back even a prediction that there should be more light coming out of the left side than the right side. Yeah. Direction. Yeah. That's true. Yeah. So whatever my detector is, it has some response function in momentum that is not spherically distributed. So it has hot spots and cold spots. If I align one of these hot spots with the average direction of the dark matter wind, then I tend to maximize my signal. But I can also then rotate my detector so that a cold spot points towards the dark matter wind. And then my signal reflects. Good. So I've talked about trans-stilbene. I haven't said what that is. And it's a chemical that involves 14 carbons. It shows itself in two different rings. So 2 rings of what would have been benzene if there were only 6 carbons, connected by 2 extra carbons and this double bond. So this long structure actually helps reduce the excitation energy because it's possible to have a ground state where the electrons are distributed across both rings, say in phase with each other, and then you might scatter to a state in which they're out of phase. So this is a fairly long distance over which to change the electronic wave structure. And this is correlated with a lower excitation energy. So this molecule has good scintillation efficiency. It's about 80% of what's possible. It easily forms centimeter cube crystals. And its excitation energy, the lowest lying excited state is at 40. To stress how easy it is to make these crystals, this picture of a glowing crystal is one that I took myself in my apartment. One point in Northwestern, we had some meeting with experimentalists and theorists and chemists to discuss the possibility of building a prototype. And one of the chemistry grad students came to this meeting with about a dozen of these crystals that he'd made himself, just grown them out of a solution. And he was passing them around kind of like candy. So
the fact that say that,
it definitely would if we were capturing our carbon from the atmosphere. We actually did this calculation and saw that if you did atmospheric carbon, then the background rate would actually be problematically large here. So the key is to use fossil fuels or fossil sources to get the carbon from. And these things are often millions of years old, and so the fraction of carbon-14 is quite low. There are some fractions of thorium or some other heavy metals that are radioactive, usually in these samples. And so one does have to ask the manufacturer to filter these out. Some of the manufacturers, like Elgin, are known to just do this for you if you ask. We had a previous version of an experiment with a kilogram of liquid scintillator, and that had been filtered with the thorium and these other heavy isotopes. So removing the radioactive isotope from the sample is possible. And even though this is a crystal, it melts at about the boiling point of water and stays liquid at room temperature until you try to crystallize it again. And so filtering out impurities in this thing is actually pretty easy. It's quite nice. Good. Yes, and a brief note about chemistry. Carbon has, between the single bonds and the double bonds, with carbon, this involves the p orbitals of the atom. So the single bonds usually form with 2 of these p orbitals overlapping the nose to nose, like in the red here. Once those states are all occupied, the remaining double bonds are using these z orbitals that come out of the plane. So those are more weakly coupled. And to a good first order approximation, the whole molecule and its low-lying excitations can be described by just 14 electrons participating, one from each carbon, only using the 2 pz orbitals. So that's the model that we used for this. It's sort of 1950s, 1960s era chemistry. So it's a good first approximation. It's probably not exactly right. It shouldn't be. But it should be good within a sort of 10% level areas. Now, why do I actually need to know any chemistry? It's because I need to know the initial and final state wave functions of the electronic system. So I can insert my favorite Feynman diagrams between momentum eigenstates of the electron. This is a very familiar calculation to us. Pull it out of test here. Other favorite textbook. But to know the momentum eigenstates of the system, when they are no longer eigenstates, requires some knowledge of the wave functions. And so this is what, in the red, is what we need chemistry for. It boils down into this form factor from an initial to a final state. This is the thing that we have to calculate, given that we plan to transfer some momentum Q into the system. The remainder of this is particle physics, and so it's easy for us. This molecular form factor is variously called the dynamic structure factor, or in some cases, the electron loss function. So it's not an unfamiliar object to dark matter directly. The key that I need from a molecule that we didn't know was going to be true when we started is we need this response function to be anisotropic, not spherically symmetric. It's entirely possible we could do this calculation and get something that's just too sphere-like. And then instead of having big asymmetries, we'll have percent level asymmetry. Not really good. And so the fact that this thing is not looking very much like a sphere is a good first sign that this will be a good detector for dark matter. In order to get a modulating signal, I do need 2 sources of anisotropy. I need it from the astrophysics, and I do from the dark matter wind. And we also need it from the chemistry. Combining those 2 together, and you get daily modulation. And here's what that could look like. In the lower plot, I've plotted the scattering rate as a function of 2 angles. It's the direction of the Earth's velocity with respect to the z-axis of the crystal. So if we pretend I put my crystal here in the room, with its z-axis pointing up, theta equals 0 means that the dark matter wind is coming from directly overhead. The azimuthal angle is what you'd expect. And what the Earth's rotation is going to do for us is it's going to take us on an orbit around the North Pole. So let's focus on the black curves for now. In this case, I've aligned the North Pole with the latitude of my detector. So here in Minnesota, I would pick maybe 44 degrees north. Then, say following the dashed line, I would start from directly overhead and orbiting around the North Pole like this to take me from the maximum rate to close to the minimum. In this case, I'm using a heavy mediator model with a 10 MeV dark matter candidate, and I see that my rate varies by 5 or 6%. How it changes as a function of time is shown above. So each of these curves corresponds to the black solid line here, or the gray solid line orbiting the minimum. And so I can see that by just changing the direction of the North Pole with respect to my crystal, if I took the crystal and then, let me see, pointed the North Pole directly at its equator. So I took my crystal and I tilted it up by 44 degrees. I could go from a plus minus 5% modulation down to a plus minus 1% modulation. This is relatively easy to arrange in the laboratory. And this is one of the first things you would actually do if you see a signal. You would change the orientation of your detector and see if its amplitude changes in the response that you'd expect. So, you can also rotate your detector in the plane. And there's a particularly interesting point in this particular particle model this approximate saddle point. And so if I align the North Pole with the equator of the detector and allowed the dark matter wind to go from its upper hemisphere into its lower hemisphere and back, I see the gray curve corresponds to the dashed lines in this modulation plot. And I see an almost perfectly 12-hour modulation. So I can get 12-hour modulation as well as 24 modulation just by rotating the crystal. So there are a lot of knobs that can be turned in the lab, probably literal knobs in this case, to change the behavior of the signal. So you don't just have to maximize. Yes, yeah, thank you for asking. Mhm. Yeah, yeah, so this band of 3 lines corresponds to either a fortunate or an unfortunate annual variation, depending on how you look at it. Just to say, a lot of the literature just says that the Earth's velocity is always 42 degrees away from the North Pole. It turns out, you can check, it's not so hard. That angle changes within a band of a bit more than 12 degrees over the year. And so in March, I believe, you follow this dotted gray line. But in June, well, I forget exactly when it peaks, but the precession of this cone opening angle varies once per year. So at the moment, the opening angle is about 46.5 degrees now. So we would actually find ourselves closer to the dashed line here. It's just something that has to be taken into account. Good. So if we were to build a detector, we don't know what its background rate is yet. That's the whole point of making a prototype. If it were 1 event per minute per kilogram of detector size, then with a detector that does not have any directionality, the exclusion line we could draw is this dashed one. It doesn't matter if we've made our detector bigger, if our noise scales with volume. So this is the best the system could ever possibly do, whether it's 10 grams or 10 tons of detector. Looking for the modulating signal, we can do much better than that. With a 10-gram size experiment, we can put a constraint that's just barely stronger. By making the experiment 100 times bigger, you get a constraint that's 10 times better. The usual root end scaling in the presence of that. With 100 kilograms, we could rule out part of this. We could rule out or detect part of this scalar freeze-out model. The yellow bands here indicate which models could be detected with a level of 3 sigma confidence. That is, you would expect that this model here, on the scalar freeze-out line, generates a signal that modulates large enough that once you've done your statistical analysis, you see that modulation by a 3 sigma level. With the Friesen model, it turns out to be even, well, it's a flatter curve, and so it's easier to rule out the whole thing on its parameter space. A 1 kilogram size detector, still with this level of background, would probe a big part of this, whereas a 100 kilogram detector would be sensitive to basically the entire line, down to its low energy threshold. It is, especially in the context of the, say, xenon experiments in LZ. They have, their event rate is at the level of 1 per year per multiple tons. This is a somewhat conservatively high background rate, but it's in line with, say, the current limit from Sensei, which is also at the 10-gram level. Their constraint is about here. Now, in my detector, I actually don't expect my background rate to scale with volume. I expect it to be driven by the dark rate of the detector's photon readout, which scales like area. So I would expect to gain somewhat appreciably by making my detector larger. But yeah.
This solar reflection already the result model to 7 years before.
Yeah, this is from the 10 to the minus 37.
Yeah.
Yeah, yeah. Yeah.
Looking at the same model.
Yeah. Yeah. Is this the cross section with the electronic scattering? Yeah, yeah. So. For this, it doesn't matter much at all. They map onto slightly different sets of non-relativistic operators. So there are some like spin couplings through the vector mediator that you can't have for the scalar. Those are often somewhat suppressed by some powers of velocity. There's one that's not. So they change in your interpretation of these constraints for your particle model, but it doesn't change very much at the level of these spin-independent scatterings. Then it makes a much larger difference. Yeah.
Is there any way?
There is, yeah. It's actually something I'm working on at the moment. That is, this is a very simplified picture, but electrons that spin the dark matter, depending on its quantum numbers, may alter the spin. If it scatters through a scalar, then some of that information must be lost because the scalar doesn't carry the angular momentum with it. But if it scatters through, say, a dark photon, then there's a potential for rather a lot of spin-dependent interactions. Spin dotted in with spin dotted in with velocity of the dark matter, spin dotted in with the momentum of the dark matter. So those are all possible. And yeah, this turns into 6 or so different plots you have to look at. The number of signal events for the black line. Yeah. It would be yeah. 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 So here here my constant level events is very high. I've run my experiment for an entire year with 100 kilograms and seeing, well, in this case, 100 events per minute for a whole year. This is now 50 million or something events. And so this black line means that I've looked for a modulation that's still a slight thing, but it's large enough that the modulation is about a square root of 10, 100 million many events. So maybe I'll call this 3,000 events. So it's a few parts in 1,000 level of modulation that I'm looking at from these dark matter candidates. But I have enough events that I can actually claim to see such a thing once I've stacked my data. I'll open the sidereal though. The background is 100 million, so this is also annual background. So this signal has to be higher than 0.4 modulation, which I count to a single level. That's right, yeah. It does, yeah. Yeah, it should also say that if I took away this background of 1 event per minute per kilogram, my constraint is then down here at 10 to the minus 42 or 10 to the minus 43. It's a substantial difference when I can operate in the background free limit. Yeah. So you always gain by reducing your background. Reducing your background reduces this dashed line linearly. And once you can no longer do that, then you require some sort of modulation. Yeah. Where would those go? Oh, yeah. If I weren't using modulation, then they just live in this dash line. And they stay there whether I make my experiment a kilogram, 1,000 kilograms. If I can't reduce that background, then this line of experimental progress is dead. Yes, if you can increase your threshold, say, for example, to get rid of the beryllium-8 neutrino, the boron-8 neutrinos in the case of nucleus scattering, then you can operate in the background free limit again. Yeah. Absolutely, yeah. Yeah. Yeah, and so Sensei's rate plots look something like a relatively deep constraint offset to the right, followed by some weaker constraints that can reach lower dark matter masses, but without the absence of background. Yeah, well, but again, if we do in fact live in this parameter space, then if I increase my energy threshold, then I'm just completely blind to this part of the parameter space. So if I want to say probe this to a breathe-out line around here, this is one way to do it. Increasing the velocity of the dark matter and looking for a contribution from the sun is the other way. Then you get the high energy threshold with different sources of background that may be absent. Good. So we are currently assembling this prototype experiment in Fermilab. It has 8 gram size samples of this trans-stilbene. Each of them is a perfect cubic centimeter. Approximately perfect. And we're using the Skipper CCD technology that Sensei and Dama use for our single photon readout. We have a single photon in the 1 electron bin, so we're not in the background free limit. But we only need some millimeters worth of this material. And so the intrinsic background from our CCD can be controlled just from its small volume compared to the 8 grams worth of trans-stilbene we have. They've designed the box that this experiment is supposed to sit in. And each of these cubes is going to be set in some sort of an epoxy with a matching index of refraction so that we get no internal reflection between the cube and its holder. And then we have total internal reflection within the cube for 5 of those 6 sides, leading to the CCD that lies directly on top. So each segment of the CCD is sensitive to a different crystal. And somewhat annoyingly for me, each of the crystals has been cut in a slightly different way so that the normal vector, which is listed here, is slightly different for each sample. On the plus side, this means that each crystal should have a distinct modulation curve, different from its neighbors, and that's something we can look for. On the minus sign, the experimentalists asked me tricky questions like, what's the best way to orient these 8 crystals that we have? And then I have to do a bunch of trigonometry. So that's a problem for me, not a problem for you. If anybody is curious to see more details about the experimental design, there's this talk by Nora Hope at a CTAD conference that you can look up. The slides are online. That's where I took this picture from. Dane Johnson is the chemistry graduate student at MIT, who originally provided me and Carlos with that sample of trans-stilbene that we photographed in my apartment. So I'd like to take a brief minute to discuss the actual rate calculation. It's somewhat annoying once you know that you have to do a bunch of rather high dimensional integrals for multiple samples of the crystal for multiple orientations in the day. This is the integral we're talking about. Where here I have the honest to goodness velocity distribution, which might be the standard Halo model with its mean and its dispersion. Or it might be some other astrophysically generated velocity distribution, say taken from n-body simulations or something complicated like that. I have my material form factor, which in principle we know how to calculate, if we help the chemists. And it remembers all of this information about the dark matter particle. Its scattering form factor which depends on even possibly spin dependence. It also depends upon the dark matter mass and the mediator mass. And energy conservation holds, and so there's something about a delta function. And so there's an effectively 6-dimensional integral that we have to do a whole bajillion many times. We have to do it for the dark matter model. We have to do it for many thousands of detector orientations. We might only test one standard Halo model, but we might want to test an ensemble of them. There's not just one excitation in this crystal. There were 8 that were relevant. So we have to repeat this calculation for each of those as well and have the results. Each of these things must be scanned over independently. And if we tried to do something like that with 100 different physical velocity models, we're staring in the face of having to do this calculation a billion times. It's a numerical integral, so each one might take a few minutes. And a billion minutes is apparently 2,000 years, give or take. Now, of course, I can go and ask for some money to put this on some supercomputers. And then I might actually convince somebody to give me CPU years worth of time. Getting 20,000 CPU years worth of time is even a gigantic ask. It's more than the n-body protein. So this would tell me that I'm sort of stuck. Now, of course, I can use the standard Halo model, reduce this by a factor of 100, but then I still need 20 CPUs worth of numerical integration. You would think that there has to be a better way. And it turns out that there is. If you were to take the velocity distribution and the momentum response function of the detector and to project them onto a basis of spherical harmonics and some sort of radial function, it turns out this problem becomes drastically simpler. Partly due to the symmetries and group theoretic properties of spherical harmonics, and partly just due to the factorization that this permits, that all of the kinematics and that 6-dimensional integral can be done on your basis functions, which you, the user, get to pick. So putting spherical harmonics into here, this scattering matrix becomes effectively diagonal in both of the angular indices, meaning that the spherical harmonic LM moment of the velocity distribution only talks to the matching LM moment of the detector. And so this is a fairly interesting physical result as well, and it's drastically reducing the computation time here. After calculating a couple of matrices, including this partial rate matrix K, defined in terms of the velocity distribution and the momentum distribution, the calculation that has to be done a billion times reduces to a simple trace over 2 matrices that are known, in this case, analytically, and in this case, it can be calculated numerically in a couple of seconds per combination model. Calculating a trace is actually really easy. You can do millions of them per second, depending on the length of the vectors. And so performing this for a billion orientations, sorry, a billion combinations of orientations and models is something that takes about 20 minutes rather than 20 years. So this has been tremendously useful for this whole experimental project. There are a couple of papers in 2023 that just go through those details. And if you happen to have encountered a linear problem that still requires substantial computational resources, there's a decent chance that your linear problem could be formulated in a similar way, particularly if there's some notion of rotations or operators whose eigenfunctions you know. So we also have a numerical code that came out officially this week called Vector Spaces for Dark Matter. And it does this projection part of the calculation, and it also does the rate part of the calculation. So that's mostly useful if you yourself plan to do any direct detection analyses. It has the benefit of allowing, say, the n-body astrophysicists, these semi-galactic scale systems. They can focus on this part. Once those velocity distributions are known, then all I would need to do as a particle theorist interested in dark matter is I can come in and supply my detector physics. I can download this vector of coefficients from the astrophysicists, and then I can use their brand new n-body simulations to just update my own results. So vice versa. If you've done a difficult astrophysics calculation, you want to know how it would affect all experiments that have ever been discussed in this context. You can also just go in and do the dot products yourself. It's very quick. So that's where I'd like to stop, at least this part of the talk. My main conclusions are we should build one of these, and it's fairly easy. That is, it's possible to get 100-gram or 200-gram samples, in this case for free from someone that Dane Johnson knew at LBNL. So these materials are easy and cheap enough that someone was willing to write on one with pen. The directional dependence can tell us rather a lot about the particle physics, as well as about astrophysics. And molecules in particular are great for the electronic scattering, as well as nuclear scattering. Now, this is a part of the talk that I didn't expect to get to today, but a molecule is a sufficiently asymmetric environment for a nucleus that kinematic scattering could also become anisotropic for, say, a diatomic molecule, or for this trans-stilbene or any other complicated system. We haven't finished the calculations for anything harder than a diatomic molecule, but we did find that the anisotropy in a diatomic system could also be on this level of 30 or 40%. So this is particularly interesting to me in the context of solar neutrinos, but that's a topic for ongoing work. So I have many slides to discuss that as well if people are interested, but I'd like to officially stop the talk here. Yes.
Maybe one natural question is, how sure are you with your background?
Yeah.
Like in terms of like cosmic rays or your background?
Yeah, so that's a great natural question to ask. So they have at least checked this for muons, and I wish I had the paper in front of me, but their anisotropy was at the level of sub-%, maybe 0.3% modulation in the muon flux over the course of the day. So there are some anisotropies there that you would expect to vary, possibly even with a sidereal day. So anything that is generated by the sun, you'd expect to follow the 24-hour cycle. And so the key to a good sidereal day analysis is to take data for 3-6 months to be able to distinguish the sidereal day from the solar one. Once you've binned over, say, a 6-month cycle, then anything that was in phase with the sidereal day at the start of your experiment has now become perfectly out of phase. And so by binning on that sidereal day, you should completely wipe out the annual signal, the solar signal. But it's not something you can do in one day or even 1 week. So another key thing that you can do in the lab is you can take this crystal and rotate it by 90 degrees. If you're seeing something that is external to the laboratory, that is not dark matter, it should not be, it should not generate a change in its event rate simply by rotating the detector. Now, unless, say, there's some radioactive paint on this part of your laboratory wall. There are some directional sources of background that would be constant. And then there are some 24-hour daily modulations that should be rotationally independent. And only the dark matter should be both. Neither, I can say. Given 3 different crystals, you could even put them each 8 hours out of phase with each other by rotating them about the North Pole axis. And so then you would see each crystal reaching its maximum 8 hours after the next one. So there are cool experimental setups you can do like this with multiple crystals that can completely veto any other sort of time varying background.
Is that part of the initial strategy? I forget how many you said.
8, yeah.
Yeah, so is that, are you trying to optimize, like different normal vectors, trying to optimize all the what is that?
Yeah.
Tell them out of phase on purpose and get there.
We haven't completely decided yet, so I'm checking both at the moment. I found that of the 8 crystals, there were 3 or 4 that really strongly cared which face was up in the lab. The way others were cut, they didn't care as much. And so I was thinking about you suggesting anyway that those 3 or 4 face up, and then the other ones that where it's a little bit negotiable, maybe we can play around with their orientations to get cool things like the saddle point with its 12-hour modulation, something approximately like it, or these fun games about putting things 8 hours out of phase with each other. But I need to make a gazillion plots in order for us to know the possibilities, and I haven't made all those plots yet. So, yeah, I should say also the experimental collaboration has been focused on characterizing the details of their detector. They're taking spectra of the scintillation light, things like this. They're trying to make sure that they can isolate the scintillation light from other sources of photons. Eventually, this is going to be placed in the dark in the sub-basement at Minos, down here. So this will shield it from a decent amount of cosmic rays. It'll be about 100 meters below ground. The big follow-up version of this experiment that we would like to have happen, we would probably even put farther underground, something like snow. So the time at which they're going to start taking physics data is still a little bit unclear, but it's measured in a few months rather than years. So at one point they discussed even starting that in March. So it's really coming soon. Tomorrow, yeah. So I don't know if they're ready to start tomorrow. Yeah. They're really focused on hitting some of these crystals with electron beams and stuff like that. And so this spring, that's my hope. Yeah.
Let's think it again. If you want to join for dinner, we'll go to 2 hours. We'll just give us very, very far flung in the future.